Good morning all. I am Dr. P. N. Mallishwari. Today I am going to give a session on Introduction to Signals and Systems. This is our first topic in our first module, and let us see about the contents involved in our first unit. Introduction to Signals and Systems, classification of signals and systems, standard signals, basic operations and signal analysis. Let us see about the introduction to signals and systems. So what is meant by signal? Where can we use the signals? Signal is nothing but a set of information, or it is a physical quantity that varies with time, space or any other independent variable. For example, x of t equal to sin t. For example, x of t equal to sin t. So here sin t is a signal, t is an independent variable, and see, for different values of t, for example t0, we have some amplitude. T0 means sin 0, 0, t1, t2, like this. See, this is the signal. So it gives some information. It is a set of information, or it is a physical quantity that varies with time, space or any other independent variable. For example, now I am talking something, means I am generating my voice signal. And in general, signals or different types. What are they? One-dimensional signal, two-dimensional signal and multi-dimensional signals. For example, if the signal depends on one independent variable, then that is called one-dimensional signal. Best example, x of t, okay, and f of x, like y of t. These are nothing but one-dimensional signals. Best examples in our daily life, AC power signal. Next one, speech signal. So those are the examples of one-dimensional signals. And here signal depends on only one independent variable. And let us see about two-dimensional signal. If the signal depends on two independent variables, then that signal is called two-dimensional signal. Best examples for two-dimensional signals are pictures, X-ray images and sonograms. For example, if we take picture, that is f of x, y. So here x and y are the spatial coordinates. And f indicates the brightness of the image. So here this signal depends on two independent variables. That's why it is called two-dimensional signal. And if the signal depends on three independent variables, then that is called three-dimensional signal. Best examples for 3D signal is color image. Color image. This color image consists of three parts. What are they? Color image consists of three parts. What are they? Green, red and blue. Those three are called color frames. If we combine those three colors, we can get white color. If we subtract those three colors, we can get black color. And if the signal depends on more than two independent variables, then that is called multi-dimensional signal. And let us see about the example of multi-dimensional signal, like video. That consists of both space and time. That depends on space and time. And let us see about the system. What is meant by system? System is a physical device that performs an operation on a signal. Here, system requires an input. By using some operation, it produces an output. For example, x of t is our input or excitation, and y of t is nothing but transformation on x of t. This transformation means some operation. By using some operation, the system produces an output. And let us see about the general example of system. Filter is one of the examples. What is the main purpose of filter? Filter can be used to remove the unwanted components. For example, if we take our water filter, it removes the impurities. And in communication system, filter can be used to reduce the unwanted frequency components. And best example, say if we take any communication system, that communication system consists of both transmitter, receiver as well as channel. So here transmitter can be used to transmit the signal. At the receiver side, receiver will receive the signal. Between these two, process should be done. Okay, process should be done through the channel. And if you take any classroom communication system, when the teacher is saying something, before reaching the students, that signal may be corrupted with some fan sound or some students' noise. Then automatically student will receive the noisy signal. So how to remove that one? By using filter. So here system is nothing but a physical device that performs an operation on a signal. And let us see about the signal modeling. What is meant by signal modeling? If we represent the signal by a mathematical expression, then that one is called signal modeling. Means modeling is nothing but representation of a signal by a mathematical expression. Best example, deterministic signal. For example, x of t equal to a sin t. So here we are representing the sinusoidal signal with a mathematical expression a sin t. Similarly, random signal. Random signal means we can't represent the signal by a mathematical expression. Random. Random means some zigzag pattern is there. Some zigzag pattern is there. So this is the best example of random signal. And let us see about the next task. Classification of signals. In general, the signal can be classified into continuous and discrete time signals. Again, this continuous and discrete can be classified into periodic and aperiodic or non-periodic signal, even and odd signal. Next, causal and non-causal, energy and power signal. Next one, sinusoidal signal, exponential signal, deterministic and random signal. Let us see the difference between continuous and discrete time signal. What is meant by continuous time signal? See, a signal which is continuously varying with time. A signal which is continuously varying with time is called continuous time signal. Continuous time signal is always represented by x of t. And here see, this is the best example, x of t equal to sin t. So here t is an independent variable. And what is meant by discrete time signal? A signal which is discretized with time. For example, this is the sinusoidal signal representation. And the signal is discretized with time. Means signal is defined at discrete instants of time. For example, nt versus x of nt. But continuous time signal is represented by t versus x of t. For example, nt. Okay, t is nothing but maybe 1 second. So simply how to write this? N versus x of n. N versus x of n. And see, this is n versus x of n. For example, n0, some value, n1, some value, n2, some value, n3, some value. So here, this is the discrete time signal representation of this sinusoidal signal. Means this one. Okay. So here, this one is called sample. So here, continuous time signal can be converted into discrete time signal. And signal is defined at discrete instants of time. For example, this is t, 2t, 3t. So for every certain interval, we have some amplitude. And it is represented by x of nt. So this is the difference between continuous and discrete time signal. And let us see about the next classification, causal and non-causal signal. For a continuous time signal x of t, if x of t equal to 0 for t less than 0, then that signal is called a causal signal. Means there is no value for negative values of t. Signal is defined between the interval 0 to infinity. There is no value for t less than 0. And otherwise, signal is non-causal. Okay, and let us see about the best example. Best example for causal signal is u of t. Where that u of t exists, u of t equal to 1 for positive values of t, that equal to 0 for negative values of t. Unit step signal exists only for positive values of t, that equal to 0 for negative values of t. Means u of 0, u of 1, u of 2 up to u of infinity is 1. Similarly, u of -1, u of -2 and u of minus infinity is equivalent to 0. So here causal signal exists only for positive values of t. Best example for causal signal is unit step signal. Let us see its graphical representation. 0 to infinite interval, its value is unity. Its value is unity. Minus infinity to 0 interval, its value is 0. So signal exists only for positive values. And let us see about non-causal signal. Non-causal signal best example u of minus t or u of minus t minus 1. Let us see where this u of minus t exists. That u of minus t equal to 1 for minus t greater than or equal to 0. Means if we neglect this negative sign, simply symbol may be changed. Means u of minus t equal to 1 for t less than or equal to 0. That equal to 0 for t greater than 0. Means u of minus t, it exists only for negative values of t. Means minus infinity to 0, value 1. No? For positive values of t, that value 0. And where this u of minus t minus 1 exists, that equal to 1, for minus t minus 1 greater than or equal to 0. Means what about t value? Less than or equal to minus 1. Less than or equal to minus 1 means minus 1. Minus 2, minus 3 and so on up to minus infinity. So the signal exists between the interval minus infinity to minus 1 and before that signal 0. So this u of t is the best example